Volumes of revolution, the shell method, part 1. Consider the region bounded above by f of x, below by the x-axis, and on the left by the y-axis. We want to revolve this region about the y-axis. If we were to use the washer method, this would be a difficult, perhaps impossible task to do. First, we'd have to split this region into two parts, the part above the dotted line I just drew, the part below the dotted line. We would somehow have to turn our function, f of x equals y, into x equals some other function of y. And then in the top part, we'd have two radii. Well, the length of the radius, although completely different, both depend on this function, x equals g of y. So let's consider an alternate method to find the volume of revolution. Instead of making circular disks, we're going to make cylindrical shells. Now we're going to start in the same way as we would with the washer method. We're going to make a rectangular cross-section. And we're going to revolve this rectangular cross-section about the y-axis. Notice that if we were to do so, we would end up with the outside of a cylinder that has a tiny width of dx. That is why we call this the cylindrical shell method, or simply the shell method. So our goal is to find the volume of these cylindrical shells. So we have the very thin outer layer of a cylinder, not the inside part, just the outer layer. It has a volume because it has a tiny width of delta x, and we want to find this volume. Notice that we could unwrap, quote unquote, this cylinder and make a rectangle. Really, a rectangle with a tiny width of delta x. And we want to find the volume of this rectangular prism. Well, notice that the height of this rectangle, which is right over here as well, is the function height at a particular x. Notice that the radius right here is x, because we are x away from the y-axis. And since we have a cylinder whose outer rim is the circumference of a circle, the length of this rectangle would be 2 pi r or 2 pi x. So the volume of one cylindrical shell will be length times height times width. And to find the total volume of the entire region revolved, we would simply add all of the tiny pieces together. So let's take a look at a specific example. Consider the graph y equals 4x minus x squared in the first quadrant. we'll do a little work to get it set up. I'll find the x-intercepts, be it x equals 0 and x equals 4. I have a parabola that's facing downwards. I'm not going to draw it to scale, just trying to get a picture. But something along these lines. And we want to revolve this region about the y-axis. Recall from above, the volume is going to be the sum of 2 pi x times f of x times dx. From some x value to another x value, which I think we can see pretty clearly is going to be 0 to 4. So plugging everything we need into our integral, we get that the volume is the integral from 0 to 4 of 2 pi times x times f of x, or y in this case, times the tiny width of delta x. Let's rewrite this so that we can take the antiderivative a little more easily. I will pull out the constant here and then distribute the x. And then do some antiderivatives. So I'll leave the constant outside. Do some power rules. And then we will finish it off by plugging in the upper limit. So I have 4 times 4 cubed. So I have 4 to the 4th over 3 minus 4 to the 4th over 4. Subtract the lower limit and simplify as desired.